So last time we talked about if we have a system, let's say undergo process or a change from one initial state to a final state, we have learned how to calculate the change of entropy delta S. So inshallah later on we can use it to calculate the entropy generation. We have learned how to calculate delta S if the working fluid is liquid or solid or incompressible substance in general. Based on the developed TDS relation, we have developed two TDS relation. The first relation delta S is function of delta U over T plus BdV divided by T. And the second relation for delta S, we have developed the relation as function of the enthalpy delta H over T plus VdV divided by T. And we have considered some special, as we said, some special cases. We have considered the first case in case when we have liquids or solid, or in general we can call it actually as incompressible substance. So when we have incompressible substance, we said this last time, incompressible, that means actually the density is not affected actually by pressure, so the density is constant and density is equal to 1 over a specific volume. So at the end we can say the specific volume for incompressible substance will be constant in this case. Type V is constant, that means actually that delta V, the differentiation of a constant, should equal to 0. So this term, if we consider this equation, so this term BdV will be 0 in this case. And in this case we can say delta S will equal to du over T, and we can just do the integration. Then if we have compressible substance, then we can say delta S undergo a process from 1 to 2. So delta S, which is S2 minus S1, will equal to integration of delta U over T, okay? And delta U for incompressible substance, as we have learned in chapter 4, delta U will equal to C average multiplied by delta T. We can take C average outside, which we get from table A3. So it will be integration of delta T over T. So in this case, it will be integration of C average dt over T from temperature T1 up to temperature T2. And we said this CV average is calculated, as we learned it from table from chapter 4, how to calculate CV average for solid or liquid. C average, we don't say CV, it is the same. For solid and liquid, it is the same. And this C average is calculated from table A3 at the average temperature, which is T1 plus T2 divided by 2 in this case. And as it is average value, then we can take it outside. So in case actually of incompressible substance, solid or liquid, the change of entropy will equal to C average multiplied by integration of dt over T. It will be integration of ln T2 over T1. And this is the first special case when the working substance is solid or liquid, or we call it actually incompressible substance. In this case, to calculate delta S will equal to C average multiplied by ln T2 over T1. But let's continue Shabab today if the working fluid actually is gas in this case. How we can calculate the change of entropy delta S. So the second special case, if the working fluid is ideal gas. Usually we consider, when we say gas, we consider it as an ideal gas. But in the application, Shabab, in the industry, you have to consider actually one of the modified equations, especially PV is equal to ZRT. Because when you calculate the compressibility factor, this will give you actually better prediction for the actual volume. So if you are working, let's say, in a factory to fill gas cylinder or something. So if you are considering the ideal gas equation, PV is equal to R2, then in this case, you will be falsely calculating the actual volume of the gas. So the actual volume may be higher in this case. So in this case, you are selling a volume, but you are giving actually higher volume because actually your calculation is wrong in this case. So when it comes to the industry and you have to calculate actual volume of a gas, in this case, I have to use a Shabab what? BV is equal to ZRT. And in this case, I have to calculate the value of Z in order to actual value of volume. Because the error in the industry will be just a transfer to money. In this case, you will be losing money in this case. So if you have an error, a small error actually in each cylinder, each gas cylinder, like propane, methane, which is used actually in the houses for cooking or something. So in this case, if you have a small percentage in each cylinder for actually massive production of large number of cylinders, so in this case, it will accumulate actually big error in this case, and it will be a big loss. But usually when it comes actually to studying here in our class, we don't actually want to bother ourselves actually with much deeper calculation. So when it comes and we say we have a gas, we consider it as an ideal gas. Type, if we have an ideal gas, the second special case, if we have actually the working fluid is an ideal gas, undergo process of change from 1 to 2, and I need to calculate delta S in this case. We have developed actually those two ds relation, and for ideal gas, we have actually one equation, BV is equal to, the ideal gas equation BV is equal to RT, and we have delta U for a gas is equal to CV, which is function of temperature dt, and delta H, the change of enthalpy of a gas, as we have learned in chapter 4, is equal to specific heat at constant temperature, which is function of temperature, CV as function of temperature, dt in this case. And delta U is equal to CV, which is function also of temperature, CV dt. CV multiplied by the change of temperature, dt in this case. But let's take those relations and here and substitute in those two relations. So in this case, we can say based on the first relation, delta U will equal to delta S will equal to delta U over T, which is CV dt divided by T plus BdV divided by BdV divided by T. By pressure over temperature will equal to what, شباب, based on the ideal gas equation, will equal to the gas constant R divided by the volume. So B over T is the same as R over V. So I can just remove B over T here, this term, B over T. So it will be equal to R divided by V multiplied by delta V. And for the second relation, delta S will equal to delta H, which is CV dt divided by T, minus V divided by T. When we divide V by T, it will equal to what? R divided by I divided by B. So R divided by B dV. So just as I replace the V over T by R divided by B, and just substitute it here in this equation. So it will equal to delta S will equal to CB dt divided by T minus R over B multiplied by delta V. But actually, I don't need actually the differential form, just I need the total form. So in this case, I will be integrating the whole terms in those equations. And in this case, we can say delta S, the total change of entropy, which is S2 minus S1, which is integration of delta S, will equal to integration of CV. This CV, شباب, is function of what? In case of ideal gas, it is function of temperature. It should be a function of temperature as we have learned it from chapter 4, equal to A plus BT plus CT square. We have learned actually this integration from temperature T1 to T2, and this integration delta V from V1 to V2. And this is also CV is function of temperature. This integration from T1 to T2 minus R integration of delta V from V1 to V2 in this case. Okay, شباب? But as we have learned, we have here this equation is function of the specific heat at constant volume and the specific heat at constant temperature. And actually, to deal with the specific heat, we have two approaches. We have the constant specific heat approach, as we have learned earlier, how to calculate delta U and delta H. We said we have constant specific heat approach, in which we can take this specific heat outside as constant. We consider it average value, and then it will be integration dt over T, which is ln T. So this is the constant specific heat approach. The other approach is variable specific heat approach. In this case, I have to take CV as function of temperature and do the integration in this case. But let's see those two approaches and see how we can calculate delta S in case when we have an ideal gas. Okay. So first of all, this is the step number 2 for ideal gas. Step 2A, when we have ideal gas, for actually is a constant specific heat approach. So we'll be considering, this is called as the approximate approach. Approximate because actually specific heat is not constant. It is function of temperature. But when we assume constant specific heat analysis, we call this is actually the approximate analysis. So if we have an ideal gas considering the constant specific heat approach, so delta S, which is S2 minus S1, will equal to integration of CV. We can take it outside as average value. It will be CV average multiplied by integration from T1 to T2 delta T over T, which is ln T2 over T1. We have another term. This is the temperature dependent term يا شباب of delta S, and this is the volume dependent term. Okay. For the second equation, this is the temperature dependent term, and this term is the pressure dependent. Because in the second case we have enthalpy, and enthalpy is direct function of pressure. So don't forget this term. So plus R dV over V. When we integrate, R is the gas constant. Integrate delta V over V, which is ln V. So plus R multiplied by ln V2 divided by V1. But based on the second equation, delta S function of CV, we can get another equation which is CV average, also integration of delta T over T, which is ln T2 over T1 minus the second term. We have negative sign R delta V over V, so it will be R, and the integration of del V over V will be ln V2 over V1. And this is the equation that we use. We have two equations. We can use either of them to calculate actually delta S of an ideal gas following the constant specific heat analysis. But from where شباب we can get CV average and CV average? Do you remember?
S3.
From where? How we calculate CV average and CV average? So those two are calculated from where شباب? From table A to B, as we have learned for the case to calculate delta U and delta H following the constant specific heat analysis. So it is the same from table A to B, T1 plus T2 divided by 2. Calculate the average temperature, go to table A to B. Depending on the ideal gas, let's say we have air, we have argon, we have nitrogen, any gas, then we can from table A to B, we can calculate CV average in this case. R شباب is the gas constant, and as you know, the gas constant we can get actually from table A1. Depending on the gas type, we can get actually from table A1, we can get the value of the gas constant. Is that clear شباب?
Yes.
So we just took the TDS relation, we went through the integration, consider CV as constant, CV as constant, take them outside, complete the integration, then we get this, get this relation actually in this case. طيب شباب, in some cases actually this is the change of entropy. This CV is calculated in what شباب? In kilojoule per kilogram Kelvin, same as the gas constant in kilojoule per kilogram Kelvin. So this is the specific entropy calculated in kilojoule per kilogram Kelvin in this case. Okay. But if I need to calculate the molar value, kilojoule per kilomole, not kilogram, so just I will multiply the whole equation by the molecular weight of the gas. If I multiply it by the molecular weight, then I can express this equation in the molar form. We have to put bar here. This is indication of the molar form, which is S2 bar minus S1 bar. This CV, when we multiply it by the molecular weight, it will be molar specific heat at constant volume, ln T2 over T1 plus R multiplied by ln V2 over V1. But instead of R, it will be what, شباب? It will be R bar or R universal. The universal gas constant is equal to 8.314 kilojoule per kilomole Kelvin. And we have the gas constant شباب. Gas constant R is equal to the universal gas constant divided by the molecular weight. And the molecular weight again is from table A1. You will find in table A1, depending on the fluid type, you will find the molecular weight is given and the gas constant is given. And the universal gas constant you will find there in the top of the table, in the title of the table. But you can keep it in mind, this is the universal gas constant. Also for the second form, it will be CV average, molar value, ln T2 over T1 minus R bar ln B2 over B1. And this delta S شباب is calculated, is the molar change of entropy calculated in kilojoule per kilomole Kelvin. When you see this bar, the molar value, that means it is per kilomole. not per kilogram in this case. And how we can convert it from kilomole to kilogram? The difference is what, Shabab? I just multiplied the whole equation by the molecular weight. So that means delta S per kilomole equal to delta S per kilogram equal to the molar value per kilomole divided by the molecular weight. Is that clear, Shabab?
Yes.
Right. This is how to calculate delta S for an ideal gas following the constant specific heat approach. Okay, this is proceed, calculate C average at P average from table A to B, then apply either one of those two equations, then we can calculate this value. Okay, but this is the constant specific heat analysis. So we have the variable specific heat analysis in this case. So variable specific heat, that means CV and CV are not constant. They are function of temperature. So in this case, we have to do this integration and calculate this value. They have already done this integration and they have listed the value in the table. So in the second case, we have ideal gas, but we'll be considering actually, instead of constant specific heat approach, we'll be considering the variable specific heat approach. It is called as the exact analysis. We call it exact analysis. Exact because actually the specific heat in this case, CV as function of temperature and CV as function of temperature. We have taken actually the real situation and we did the integration, then we have calculated delta S in this case. By delta S will equal to what? We have two equations to delta S, two TDS relation. For the exact analysis, I would be just considering the second relation. No need to take the two relation. For the approximate analysis, we have considered the two equations. One is function of CV and one is function of CV. For the exact analysis, I would be considering only the second one, which is function of CV. So delta S will equal to delta H, which is CV as function of temperature dt divided by T, this integration from T1 to T2, minus R multiplied by ln B2 divided by B1. Okay, integration of delta B over B, it will be ln B2 over B1. And this is how we can calculate delta S for the exact analysis. But we have to get this value of CB as function of temperature and do the integration. Actually, they have tested different gases, and they came up actually, this is the equation that we have developed for the constant specific heat approach, and this is the variable one. They have done, Shabab, already this integration for any gases, for different gases, for a range of temperature from 0 to any temperature. So this integration will equal to, Shabab, integration from 0 to T2. This integration, CB of T dt over T. If we have CB as function of temperature, we can do this integration multiplied by dt over T and do the whole integration from 0, the reference temperature, 0 Kelvin to temperature T2, minus the integration from 0 to T1, CB as function of temperature, dt over T. They have done this integration. And they have listed all of these values actually in tables from table A17 to A25. Okay? For table A17, you will find for air in table A17, for a range of temperature starting from 0 and go on, you will find the value of the reference entropy, reference to the 0 base, is given in this case. Okay, so if at temperature T2, you can go to the table, this integration already has been evaluated, and they give actually this value. At temperature T2, we can get the value S02. We call it S0. And at temperature T1 from the table, we can go to the table and we can get the value of S01. So this term, we call it S02. And this term, we call it S01. So we can just replace this integration by S02 minus S01. S02, which is actually the reference entropy, which is integration from 0 to T2, CB dt multiplied by CB as function of temperature multiplied by dt over T. Do this integration, you have already done this value and listed this value in the table. We call it S02 at the temperature T2. So in this case, given the temperature, you can go to the value to the table and get this value, either the temperature T2 or the temperature T1. If the working fluid is air, so I will be using table A17. If it is another working fluid, then I will be searching from table A17 to A25. And in this case, I will locate the table, and at the given temperature, we can get S02 minus S01. And this is the Shabab delta S. But be careful. Usually in your exam, just to say delta S, go to the table, A17 to A25, get S02 and S01 at the given temperature, and this is delta S. And you just forget about this term. This Shabab S0 is the temperature dependent part of the entropy. Still, we have pressure dependent part term. So you will get those two terms from the table, and you have to add here minus R ln B2 over B1. Okay, and this is the exact analysis approach. Okay, is it clear, Shabab?
Yes.
So when you go to the table at the temperature, you will get S0, which is the reference entropy. State 2, and that is state 1. But delta S, you don't have to forget actually this term. There is another term. Minus R ln B2 over B1. But Shabab, if you look at this table A17, look at this table A17 for air. You will see here we have learned in chapter 4 how to calculate H and how to calculate the internal energy given the temperature. Here in this table, you will find S0 also is listed in this table. So at a given temperature, I can get the value of S0. Relative pressure and relative specific volume, I will be talking about it today if we have time. Okay, but this is not the reduced pressure and reduced specific volume. This is something else. Reduced pressure and reduced specific volume from a chart A15. Regarding the modified ideal gas equation, BV is equal to ZRT. But here B relative and V relative, those are regarding the isentropic process. If we have ideal gas undergo isentropic process, I will be talking about it today. Yeah. Okay. But if you look for table A17, you will find the entropy is given in kilojoule per kilogram Kelvin. Okay. So I can use this equation. But let's move to table A18. If the working fluid, let's say for nitrogen, see here the entropy is given what? The molar value. And like this actually table from A18 to A25, it will be the molar, in this case the molar entropy is given, kilojoule per kilomole. But we can write this equation in the molar form, just to multiply the equation by the molecular weight. So it will equal to S02 bar minus S01 bar per mole, minus R multiplied by the molecular weight, it will be R bar, or the universal gas constant, multiplied by ln B2 over B1. So if the working fluid is not air, any other gas, and I use table from A18 to A25, I will be calculating the molar value.
Doctor,
because this value listed in the table is the molar value. Yes, sir?
We can't see the ball.
Oh my God, so sorry for that. So this is delta S, the molar value will equal to S02 bar minus S01 minus R universal, which is R bar, 8.314 kilojoule per kilomole Kelvin. So when the working fluid is not air, and I have to use table from A18 to A25, I will get the molar value from the table, okay? And in this case, this will be R bar, not R. I have to multiply the equation by the molecular weight. Then I calculated delta S in kilojoule per kilomole Kelvin. But I need to calculate delta S. So at the end, you can just say delta S will equal to delta S per kilomole divided by what, Shabab? Divided by the molecular weight. And the molecular weight, depending on the working fluid, I can get from table A1. Is it clear, Shabab?
Yes, clear.
Ahmad, is it clear?
Yes.
So, Shabab, you will see it. We have a lot of equations, but just it's very simple. Just I will start from the TDS relation. Then I can develop the equation, either for the exact, the approximate analysis constant specific heat, or for the variable specific heat. I have developed the equation. I don't need to remember or to memorize anything. Okay? Let's solve an example to see how we can proceed with that. Here is an example, Shabab. So see in this example, We have air is compressed from an initial state 100 kilopascal and 17 degrees C to a final state 600 kilopascal and 57 degrees C. And we need to calculate the entropy change of this air. So the working fluid is air. We need to calculate the entropy change based on the property from the table, which is the exact analysis, and based on the variable specific heat approach. So can we, ya shabab? So look here. Because inshallah in your final exam, I will just give you a problem like this one. This is a compressor. I will ask you to calculate the work of the compressor, like what we have learned in chapter 5. Apply the first law, Q dot minus work dot equal to M dot delta H. I will calculate the work in this case. Then I will ask you to calculate the entropy generation, which give indication about the losses within this system. To calculate the entropy generation, you will be asked to calculate delta S. In order to substitute in the equation how to calculate the entropy generation. We will learn this inshallah later on. But this is the sequence of the problem. You have open system compressor, apply the first law, calculate the work. Then I will ask you to calculate the entropy generation. To go and calculate the entropy generation, you need to calculate delta S. But the working fluid is air, that is mean it is an ideal gas. So which approach I have to follow? I will tell you in the exam, either the constant specific heat approach or variable specific heat approach. Properties, as we said, for the constant as a variable specific heat approach. So from table A17, this is equation delta S shabab, as we said, delta S will equal to S naught 2 minus S naught 1 minus R ln B2 over B1. Type R, we can get R from where, shabab? For air, it is equal to 0.287 kilojoule per kilogram Kelvin. If you don't remember this value, you will find it in table A1. For air, you will find this is the value of the gas constant. And we are given B2 and B1, so it will be ln B2 over B1. They should be both of them in kilopascal. You can just substitute. But what about this term S naught 2 and S naught 1? At temperature T1 equal to, this value is equal to 290 Kelvin. Then we can go to table A17. At temperature equal to 290, this is table A17. Now this is 18. So table A17 for air. So at temperature equal to 290, here it is. I can get the value of S naught, which is S naught 1, 1.668. This is the value of S naught 1. Like this, at temperature T2, we can get S naught 2. Then we can calculate delta S in kilojoule per kilogram Kelvin. Following the constant specific heat analysis, so in this case, delta S will equal to, we can consider we have developed the two equations for here. One is function of CV and one is function of CB. You can use either two of them. So usually we stick to the CB. You can just take this. So delta S will equal to CB average ln T2 over T1 minus R ln B2 over B1. And CB average, we can calculate at the average temperature from table A to B. So here, CB average, shabab, we have the temperature at the inlet 290 and at the outlet it is 330. Okay. So in this case, we can calculate the average temperature between 290 and 320 or whatever. Then I can calculate the average. Take this average temperature, go to table A to B. For air, you can get the value of the specific. If there is a table in table A to B sub-table for air, then we can calculate at the average temperature. We can calculate the average specific CV. Get it from the table and do the integration. It will be CV. So this is the average temperature, T1 plus T2 divided by 2. I will be going to table A to B. The working fluid is air. You will find sub-table in table A to B at this average temperature. Then you can calculate CBR. You can get. Please try to practice this. Type I need to calculate delta S based on the constant specific heat approach. It is CB average ln T2 over T1 minus R ln B2 over B1. So just it is substitution. We have T1 and T2. It should be a shabab in Kelvin. Both of them should be in Kelvin. And this R we can get from table A1 0.287 kilojoule per kilogram Kelvin. We have B2 and B1, then we can calculate delta S. Is it clear, shabab? So inshallah we'll be using this delta S in order this term will be calculated. In order to calculate the entropy generation, inshallah, we'll learn how to calculate the entropy generation by the end of this show. Is that clear, Shabab? No.
Delta be minus. Okay.
Delta S, yes. Delta S can be positive value or negative value. This can be positive or negative, depending on the heat transfer. Is it positive or it is negative? Okay, because delta S is equal to integration of delta Q over T. This is the heat transfer from outside the system. Okay, plus the entropy generation. This term entropy generation is the losses, which should be there. This term should be always a positive value. It cannot be a negative value for any system, because it is depending on the value of the losses, which is consumed by the molecule. So this is always positive value. But this term may be positive depending on the direction of the heat transfer. If it is added, it is positive. If it is rejected, it is negative. So that means we have two terms. One positive, always positive, but this one may be positive or negative. So that means delta S, in this case, may either be positive, may be negative. Delta S. But entropy generation is always what? Is always positive value. Okay? And for an adiabatic system, if the system is adiabatic, so the first term is 0, and the entropy generation is positive, that means delta S should always be what? Should always be positive value. Okay, Shabab? Delta S, if the system is adiabatic, delta S should always be a positive value. Okay? Because the first term, which is delta Q over T, is 0 in this case. So we'll be left with the entropy generation. And this term is always positive value. So for a adiabatic system, delta S should always be a positive value. But for the atmosphere, Shabab, we are living in, if we look at our atmosphere here, the Earth, look at the Earth. So Earth, usually, actually, we can assume this is something like a ball actually existing actually in this space, wide opening space. So usually we can say this Earth is a kind of adiabatic system. Even it is not adiabatic, because actually the sun here, it gives actually some heat which come into cross the atmosphere and they come into the Earth. Some heat is absorbed and some heat is trying to be rejected to the space again. But as I told you earlier, due to the emission, we have carbon dioxide layer here, and this is what's called actually the global warming. This carbon dioxide layer here prevents the heat reflected back to the space from being actually crossing the atmosphere. And that's why the atmospheres get hotter, and that's why we have global warming. So global warming mainly due to the emission of carbon dioxide, which create a layer here around the Earth, and they prevent actually the heat to be released again to the space. And that's why we have the global warming. So we can assume the Earth as a adiabatic system. Even it is not adiabatic, the case is worse. We have global warming, even the heat actually is increased. Adiabatic means we don't have heat transfer, either here or here. No, we have heat transfer and we cannot reject it. So always actually this globe actually is, as the Earth actually the temperature is even increasing. So if we assume, the minimum case we assume it is adiabatic, the heat here is rejected, able to be rejected to the space. Same input heat has been rejected. So it is adiabatic. But this is not the real case. So that means the entropy of the Earth, or our Earth, actually should equal to the entropy generation. Entropy generation is any process in our Earth should result in entropy generation, like generating electrical power. So in this case, we have to have built a system, and in this case, we should have some losses in this system and some entropy generation. And then we release actually the exhaust gases at the end to the atmosphere. So in this case also, we have some losses to the atmosphere, some heat is lost to the atmosphere. So in this case, we have some entropy generated as well. So that means the entropy generation of the atmosphere is always what, Shabab? Is always what?
Positive.
Increasing. Even if you did a process trying to reduce the entropy, this will be a process resulting in increase of the entropy. So even any trial trying to reduce the entropy will result actually in an increase of entropy. So there is no way actually to reduce the entropy, because usually we have a process. and any process should result in entropy generation, some losses. So entropy will be increased. But if I tried to reverse this process back, the process is not reversed. When you try to reverse it to reduce the entropy, actually this process as well is irreversible. So it will result also in entropy increase in this case. And there is some idea I believe on. If you look at the entropy curve, it is a kind actually a curve with actually a point here. The point actually is that the curve actually is flipped. So usually if you are going in this direction, based on the second law of thermodynamics for adiabatic system, delta S should always be positive. So we are moving in this direction until we reach a critical point. At this critical point, we cannot move further on, because any movement here in this curve will result in delta S as negative value, and this is actually does not satisfy. This is a clear violation of the second law of thermodynamics. That means that it's going in this direction. When we reach actually this critical point, there should be actually a kind of critical mass or something for this Earth. So there should be a kind of destruction in this case. So the case cannot go forever. We should not have entropy is increasing for our Earth, and it is going actually forever. No, there is a point here at which we should reach actually a kind of critical mass or something, and at which actually there is a kind of destruction to the Earth should happen at this stage. Okay, Shabab. So based on the second law of thermodynamics, we have to understand actually that there is a point actually here, equilibrium point, at which actually we cannot move further and we cannot get back. And even if you are trying to get back, in this case actually this will result also in entropy increase. So at this point we cannot move further. So what I wanted to say, Shabab, is that we have to be destroyed one day. This is what I believe on. Okay. But do you understand this point?
Yes.
So anyway, this is something I just tried to get you outside the mini equation I have developed here. But let's get back again to the equation. Okay. But if we have an isentropic process, so case 2 is ideal gas. We have considered case 1 incompressible substance, liquid or solid, how to calculate delta S. Case 2, when we have an ideal gas, and we have considered constant specific heat and variable specific heat. Case 3, we have also an ideal gas, but undergo an isentropic process. So if we have an isentropic process, also we have specific heat analysis, so constant specific heat. Following the constant specific heat analysis, we have developed the two equations. For this case, we said delta S is equal to CV average ln T2 over T1 minus plus R ln V2 over V1. Okay. We have another equation, CV average ln T2 over T1 minus R ln V2 over V1. For an isentropic process, this equation should equal to 0, and this equation should equal to 0. Delta S is 0 because the entropy is constant. Isentropic means the entropy is what? Constant. Or delta S is equal to 0. So I equate this equation with equal to 0. Let's consider this equation first. So we can say ln T2 over T1, that should equal to minus R over CV ln V2 over V1. Is it, Shabab? Is it?
Yes.
So can we just remove this negative sign, multiply the whole, this one by negative sign, take it inside the ln, so it will be what? V1 over, and instead of V2 over V1, it will be V1 over V2. Is it correct, Shabab? Because ln V1, V2 over V1 is ln V2 minus ln V1. So if I took the negative sign inside, so it will be ln V2 over ln V1 over V2. Sorry, ln V1 minus ln V2. Or we can just say ln V1 over V2. Is it correct?
Yes.
So can we take this R over CV here as a power? So it will be ln V1 over V2 to the power R over CV. So now we have ln T2 over T1 is equal to ln V1 over V2 to the power R over CV. So that means actually T2 over T1 is the same as V1 over V2 to the power R divided by CV. Okay. طب for an ideal gas يا شباب. Okay. We have R, the gas constant. We said this in chapter 4. R, gas constant, is equal to the difference between CB minus CV. And the specific heat ratio is CB over CV. Okay. So just divide this equation by R. So CV over R will equal to, so just divide by CV. So divide the whole equation by CV. So this equation is divide by CV. So this term will be 1. And this term divided by CV will be CB over CV, which is K. So we have here K minus 1. And this is R over CV. So R over CV will equal to CB over CV, which is K, minus CV over CV, which is 1. So R over CV is equal to K minus 1. K is the gas, is a specific heat ratio. And this K, شباب, is calculated from table A to B. Depending on the working fluid, at the average temperature, I can get the value of the gas constant K. It's not يعني function of temperature. At any temperature, you can get it from table A to B. This is the gas constant K. But R over CV is equal to the specific heat ratio K minus 1. And this is the first isentropic relation. If we have an isentropic process, I said to you, we will develop the isentropic relation, how we can relate the properties. So in this case, we can say T2 over T1 will equal to V1 over V2 to the power K minus 1. And this is, شباب, the first isentropic relation. Okay? So what about equate the second equation? Consider the second equation. We have two equations for delta S. Consider this second equation, equate it to 0, and go through the same process so we can get a relation between temperature and pressure. And in this case, we can develop the second relation, which will be T2 over T1 will equal to B2 over B1, using this relation R equal to CB minus CV, and the key is CB over CV. This will be R over CB. R over CB is equal to K minus 1 over K. Then we can say T2 over T1 will equal to B2 over B1 to the power K minus 1 over K. And this is the second isentropic relation. But second isentropic relation following what, شباب? Following the constant specific heat approach. Inshallah, maybe next time, because I see the time is just going. So next time I will be considering isentropic process of ideal gas, but following the exact approach. Okay? But this next time. So look at those two relations. T2 over T1 is equal to this term, and T2 over T1 is equal to this term. That means, شباب, what? B2 over B1 is equal to V1 over V2. It will be, we can take this to the other side, it will be to the power K. And this is the third isentropic relation with following the constant specific heat approach. So if we have an ideal gas, undergo a process, isentropic process from state 1 to state 2, then in this case we can relate the temperature with pressure with volume using actually those three relations. We can say T2 over T1 for an isentropic process is the same as B2 over B1 to the power K minus 1 over K. K is the specific heat ratio calculated from table A to B. T2 over T1 is the same as V1 over V2 to the power K minus 1. And we can get the third relation to relate pressure and volume. So B2 over B1 is equal to V1 over V2 to the power K. Okay. So if I give you the condition, let's say pressure B1, temperature T1, and specific volume V1, then in this case you can apply the isentropic relation to get actually the final pressure, final temperature, and the final specific volume. Okay. But can we generalize this relation, شباب? So B2 over B1 is equal to V1 over V2 to the power K. We can say B2 V2 to the power K will equal to what? B1 V1 to the power K. or we can say in general for an isentropic process that BV to the power K is constant at any state, either 1, 2, 3, or any state. So BV, based on this relation, BV to the power K will be constant for an isentropic process. But for this process, based on this equation, T2 over T1 is equal to B2 over B1 to the power K minus 1 over K. We can make it B1 over B2. Can we? But we should have what? Negative sign here. Okay? So we can say in this case T2 B2 to the power minus K minus 1, it will be actually 1 minus K divided by K. So this will equal to T1 B1 to the power 1 minus K. Or we can generalize, we can say T multiplied by B to the power 1 minus K over K. That should be constant at any case. Unlike this, it will be T2 V2 to the power K minus 1 equal to T1 V1 to the power K minus 1. Or we can say T multiplied by V to the power K minus 1. That is also constant for an isentropic process. So those are the generalized equation. This equation, TV to the power K minus 1 is constant. TV multiplied by pressure to the power 1 minus K over K is constant. And the BV to the power K is constant for an isentropic process. For the polytropic process, it is similar to the isentropic process. It will be the same relation. But polytropic, we will just replace K by N. N is the polytropic index. Do you remember the polytropic process? BV to the power N is constant?
Yes, but
Okay.
what's different?
The difference here is actually in this case, the value of a specific heat ratio is not actually, N is not equal to K. So actually the isentropic process is a special case in which the value of the polytropic index is equal to the specific heat ratio. And the isentropic, the main difference is the polytropic process is not actually a adiabatic process, but the isentropic process is adiabatic. So if we have isentropic process, this process is what? Is reversible, and this process is adiabatic. So we don't have heat transfer. Q is equal to 0. But in case of polytropic, we have heat transfer. And this is the main difference. But in terms of those equations that we have developed, it doesn't differ. I will just replace K by N. But you have to understand the concept that isentropic, in this case, the value of N is equal to K, and isentropic process is an. Is it clear, ya shabab? Or just to get mixed?
So when the process is adiabatic, N equal K.
N equal K, and we call it isentropic. But the general case is the polytropic process. N can be actually any value greater than 0. But we have heat transfer. Is that clear, ya shabab?
Yes, clear.
Yes.